pretty mercury vapor glow with orange cathodes. Here's a quick little teardown. These UVC phone sterilizers got quite popular during the pandemic. Picked this one up at the thrift store for dirt cheap, so time to check it out. It caught my eye because it uses real mercury vapor lamps as the UVC source and apparently has an extra incense function, whatever that's supposed to entail. It came with an instruction manual for a completely different phone sterilizer, and there's no model number or anything, so I'm going in blind. Did find a few similar models online, though many are not available anymore, and I couldn't find any sort of owner's manual. Takes micro USB as power, and this iPad charger can deliver the required 2 amps at 5 volts. Using my portable watt meter to keep an eye on it. No draw when first plugged in, though the indicators light up briefly, so someone's home. Turning it on, and it draws 5 watts, but oddly enough, the UVC lamps don't illuminate. Until a minute later, when the power draw jumps up and the lamps finally light. The cycle continues, so the issues may have something to do with the cable I'm using. Dug out another cable, and the lamps now light immediately. The incense function apparently uses this little chamber in the middle for essential oils, in case you wanted your phone to be perfumed. Pressing the corresponding button causes a small power draw and the chamber warms up. At least it doesn't seem likely to catch on fire. Time to take it apart, and hope it goes back together again afterwards. Screws on these things usually hide behind the rubber feet. 4 were obvious and easy to get to, other 2 are recessed and had to change screwdrivers. Case comes apart easily, though the cable for that fan on the bottom tries to snag. Though, wait a minute, that's a tiny speaker, not a fan, and it's not even plugged in. Factory defect? Or shipping damage? Or what? Think this thing was supposed to chime or something when the cycle completes. The main body has a heater pad for the essential oils, not well secured might I add, a circuit board, and the 2 teeny tiny cold cathode UVC lamps, 1 on each side. Circuit board's pretty flimsy, so I'm extra cautious in unhooking the connectors, though it's nice they included connectors rather than soldering everything directly to the board. Not a whole lot to this thing. Low cost reigns supreme. On the other side of the board are just some traces, the buttons, and LED indicator lights. Looks like the microcontroller drives each LED independently, 1 pin per. Only some of these ICs have labels. U1 does not, and I'm assuming that's a microcontroller. C6 is a 19 microfarad decoupling cap. U2 to the right also has no markings, but appears to be an amplifier for that speaker. It may be based on an op-amp, but pin-out and external components are different. In fact, it looks to be a dual-channel amp operating in bridge mode. Pin 8, output 1, goes to one side of the speaker, while pin 6, output 2, goes to the other side. There's a driver in there that feeds inverted signal to one channel to maximize the headroom available and spread power dissipation across 2 sets of components. It's only got a single 47K resistor R19 from input to ground. C7 is a 19 microfarad decoupling cap on pin 7, and C8 is a 17 nanofarad to ground on pin 4, which I'm calling a stabilizer. U3 to the left is an ATM-TC086-24C08N, which is a 2-wire serial EEPROM communicating with the I2C protocol. It can store 1024 bytes configured as 64 pages of 16 bytes each. C10 is yet another 19 microfarad decoupling cap. R12 is a 4.7K pull-up on the clock on pin 6, and R14 is the same value as pull-up on data pin 5. Pins 1 through 4 are tied to ground. Interesting, the microcontroller itself lacks sufficient ROM, though if sounds are involved, perhaps it was cheaper to add U3 rather than upgrading U1. Q3 over here is an A1 SHB P-channel MOSFET for driving the heater. R10 is a 1K ohm gate resistor, R11 is a 47K pull-up. Q1 in the middle is another of the same for switching power to the UVC lamp driver section. R13 is gate and R3 is pull-up, same values as for Q3. Q2 and Q4 are 2 SD882 NPN power transistors for driving the center tap transformer, with center tap fed 5 volts when Q1 is on. R1 and R2 are 560 ohm base resistors. A feedback winding with inverted phase is connected to the bases. C3 sits across both collectors and the primary winding for tuning. The 0.1 microfarad C9 goes to ground as a bypass cap. There's no markings and I can't get a reading on C3 without pulling it from the circuit. The inductance of the primary reacts with the AC signal my meter uses for capacitance measurement, so it can't get a lock. When power is applied via Q1, both bases see identical current. But one transistor will conduct more than the other as individual parts will exhibit small variations in gain. In this example, let's have Q4 conduct more. Imbalancing current in the primary causes a magnetic field in the core, inducing current in the other windings. The feedback winding with opposite phase acts to reduce base current to Q4 and apply more base current to Q2. Q2 will then conduct more, causing more core flux and more induced current in the other direction. This then applies more base current to Q4 and removes more base current from Q2, and so on and so forth. The circuit rapidly begins to oscillate, driving the transformer primary with high-frequency AC. The secondary winding steps up the voltage to likely a few hundred volts, enough to strike the lamps, which are driven in parallel with the 90 picofarad C1 and C2 for current limiting. Interesting to see how many components have been removed to cut costs: reservoir capacitor, a smaller decoupling cap. They even cut R16, R17, and R18 on the high voltage side. R16 and 17 were to connect the high voltage to the positive DC rail, and R18 would have connected to ground. Not quite sure what the goal was here. If somebody can offer some insight, drop a comment below. The big USB port is simply for charging another device, though I pity the power supply. The unit draws almost 2 amps by itself, and there's no limiting circuitry. It could easily overload the power supply or cable where a UV cycle started while another device was plugged in. Time to put it back together, turn it on, and... oh! That's loud. Whoever unplugged the speaker made the right move, and whoever chose the gain settings done goofed. That's jarring. I'm just gonna unplug the speaker again. Moving on, this thing has no safety, so time for a peek at the UVC goodness. I got my goggles on, and this is a very low power device, but I'm still only going to have a glance. Very pretty mercury vapor glow with orange cathodes. Coal cathode is somewhat of a misnomer. The current passing into the gas causes significant heating. Coal cathodes are simply not electrically heating with a filament or other external means. Instead, a coal cathode lamp is driven at sufficient voltage to strike and sustain the discharge without any active heating. It still works when I put it back together, minus that speaker, which will remain disconnected for all of eternity. Not wholly sure what I'll use this thing for, or if I'll yoink parts from it in the future. Still, could be handy to have around a UV source if masks get scarce again. Thanks for watching. C8's a 17 nanoampere...